Imagine looking out at your farm dam during a really crippling drought here in South Africa.
Mm-hmm.
The water level has been dropping for months, but the wind has finally died down.
Right.
And the surface is settling. It looks peaceful, idyllic even.
Yeah, on the surface.
Exactly. But beneath that still warm surface, a microscopic threat is multiplying.
Mm.
And it's one that can wipe out an entire dairy herd in a single afternoon. So today, we're doing a deep dive into the murky, toxic reality of surface water.
Yeah, because when the rains fail and those boreholes start, pulling air or dropping in pressure.
It happens to everyone eventually.
Right, eventually. Farmers have absolutely no choice but to turn to their dams and rivers. And the fundamental problem with surface water is that it is not a static resource.
No.
Unlike a borehole, which has this massive geological buffer protecting it from sudden shifts, surface water is entirely at the mercy of the elements. It is essentially whether you can pump.
Whether you can pump, I like that phrase.
Yeah.
But it's also terrifying when you consider what the weather actually looks like during a drought cycle. And that is really our mission for this deep dive.
Mm-hmm.
We're extracting the vital, practical steps from an incredibly important article. It's titled Farm Dams and Rivers: Mud, Algae, and Making Surface Water Safe.
A very necessary read.
Absolutely.
Yeah.
And by the way, for anyone wanting to see the hard numbers, the historical data, and the treatment guidelines we are about to unpack, you can find this written article in the knowledge base on the DWT website.
Yeah, I'd go so far as to say it's mandatory reading if you manage livestock.
Oh, for sure.
Because since surface water changes with the weather, you really have to design your water systems for the absolute worst case scenario.
Right.
A system built for a pleasant, sunny average.
The idyllic day we just talked about.
Exactly. That system will fail catastrophically when the weather turns.
So because it's tied to the weather, let's start with what happens when the weather goes wild and dirties the water.
Okay.
Because before we even get to the toxic threats, we really have to talk about mud.
Right. And the scientific term we have to grapple with here is turbidity.
Turbidity.
Yeah. Turbidity is simply the measure of how much suspended mud and fine, invisible particulate matter the water is holding on to.
Okay.
And we measure this in nephelometric turbidity units, or just NTU for short.
NTU. Okay, so give me a sense of scale here.
Sure.
What does a typical South African river look like on that NTU scale?
Well, the volatility is staggering.
Yeah.
The source text highlights the Velbedock Dam on the Caledon River as a prime example of this.
Okay, I know that area.
Yeah. So in a single year, as storm flows came raging down the catchment, the raw water in that system swung from 200 NTU.
Which is what exactly?
200 is already quite cloudy.
Okay.
So it swung from 200 NTU all the way up to 90,000 NTU.
Wait, 90,000?
90,000.
If 200 is visibly cloudy, 90,000 sounds less like water and more like a mudslide.
It basically is.
How does a pump even move that?
It barely does, honestly. It is a catastrophic load of silt, suspended solids, and debris. It's liquid mud.
Wow.
And to put that 90,000 NTU into perspective, we have to look at the Water Research Commission.
So WRC.
Yes, the WRC. They have a strict treatment guide for small water supplies known as TT 18102.
Okay.
And that guideline draws a very hard line. It states that raw surface water above just 50 NTU needs a full multi-stage treatment train.
Just 50.
Just 50. Not just a simple inline filter, but a full treatment process.
Okay, let's unpack this. The WRC says anything over 50 NTU needs full treatment.
Right.
And a river can hit 90,000.
Yeah, in a flash flood. Easily.
So if you're a farmer pulling from a system like that, you can't just go buy a filter big enough to stop a literal mountain of mud.
No.
It would plug in, what, 10 seconds?
It would fail instantly. You simply cannot physically filter 90,000 NTU.
So what do you do?
Well, the solution isn't mechanical. It's geographical. The dams themselves actually have to do half the work for you.
Oh, I see.
Yeah, a large, still farm dam acts as a massive settling basin.
So you aren't filtering it, you're just letting gravity do the heavy lifting.
Exactly. The water you draw from a quiet dam is going to be infinitely clearer than the raging river feeding it.
Because the gravity drops the heavy silt out of suspension over time.
You've got it. But this brings us to the golden rule of farm water design.
Which is?
You must always size your treatment system for the dirtiest week after a storm.
The dirtiest week.
Yes. If you design your system based on how the dam looks in midwinter when it's crystal clear.
When it's beautiful and blue.
Right. That system will be completely overwhelmed the moment a summer flash flood hits the catchment.
And you'll end up pumping liquid mud into your trucks.
Exactly.
Designed for the dirtiest week. Okay, so storm runoff, bringing in obvious heavy mud, is one extreme.
Right.
But let's look at the other extreme. The storm passes, the drought sets in, the mud settles out, and that dam starts shrinking under a baking sun.
Yeah. And this is where the threat profile completely shifts. As the water level drops and the heat rises, the dam becomes the perfect incubator for blue-green algae.
Okay, blue-green algae.
Scientifically, we call this cyanobacteria.
Cyanobacteria. And we know a shrinking dam gets hot and still, which is a crisis for the farm. But from the perspective of the cyanobacteria, it's not a crisis at all, is it?
Not at all.
It's basically an all-you-can-eat buffet.
It is their ideal environment. The water is shallow, it is perfectly undisturbed by flow, it is incredibly warm.
Right.
And because the water volume has evaporated, all the agricultural nutrients...
Like the fertilizers and manure that washed in months ago.
Exactly. All of that is now highly concentrated in that shallow water.
And it's not a subtle, invisible threat either, right? The source material describes the visual cue perfectly.
It really does.
It literally looks like someone spilled bright green paint, or maybe a thick pea soup, and the wind just blew it against one bank of the dam.
Yeah, that green paint scum is the undeniable warning sign. And we have to take it seriously because certain strains of this algae release microcystin.
Microcystin.
Yes, which is a devastating, fast-acting liver toxin.
Oh, wow.
And the historical record in South Africa is grim. I mean, this isn't a modern phenomenon.
No.
Since the 1920s, farmers around the Pans in the Free State and Mpumalanga have documented unexplained livestock deaths linked to these blooms.
Right. The text mentions the Val Dam bloom of 1942 to 43.
Yes.
Where the wind literally moved the scum from one bank to the other, and the livestock deaths just followed the wind direction.
Exactly, following the wind.
But the anecdote that really stopped me cold was the Corridao tragedy in 1996.
Yeah, Corridao. That is the textbook case study of how fast and how hard this toxin hits.
Walk me through what happened there.
Well, a bloom formed in a single cement reservoir. Just one.
One reservoir.
Right. And from that one isolated water point, 290 berry cows in milk died.
Good Lord.
And another 70 were so severely poisoned they had to be slaughtered.
290 dairy cows in milk.
It's unthinkable.
You really have to pause and think about the sheer financial and emotional devastation of that for a farmer.
Definitely.
I mean, generations of breeding, millions of rand in production, completely wiped off the map because the water in one cement reservoir turned green.
Just one reservoir.
It completely justifies why the South African livestock guideline is so uncompromising. The rule is simply no visible scum, zero tolerance.
The science demands that zero tolerance approach.
Right.
Laboratory tests show that a count above 2,000 microcystis cells per milliliter means a bloom is actively building.
2,000.
Yeah, and at that density, you can go from clear water to a lethal scum in a matter of days.
So if a farmer drives out on a Tuesday and sees that green paint forming on the water, the immediate physical fix is just a fence, right?
Yes.
You have to physically separate the herd from the hazard.
Fencing the water point off so the animals cannot reach it stops the deaths immediately. You isolate the hazard and switch the herd to an alternative supply, like a borehole.
Okay, isolate the hazard. If I'm a farmer, once I've got the fence up, my natural instinct is going to be to fight back.
Of course.
I want to save my dam. My first thought would be to go down to the co-op, buy a heavy-duty algicide, and bomb the dam to kill the bloom.
Which is the worst possible thing you could do.
Really?
Yes. Here's where it gets really interesting and terrifying. There is a paradox with cyanobacteria. Killing the algae is the exact trigger that releases the poison.
Wait.
Yeah.
If the microcystin toxin is locked inside the living cells of the algae, and I bomb the dam with algicide,
You're bursting the cells.
I'm basically blowing up the cell walls and dumping all that venom straight into my own water supply, aren't I?
You weaponize your own dam.
Oh, man.
You take a localized scum problem, which was just floating on the surface.
Right, push to one side.
Exactly. And you turn it into a fully dissolved toxic soup that mixes into the entire water column.
That's horrifying.
So the precautionary guidance dictates that if you do make the decision to treat a bloom with algicide, You must keep all stock off that treated water for 2 to 4 solid weeks,
2 to 4 weeks.
just to let the toxin naturally degrade.
2 to 4 weeks without a main water source during a drought is a death sentence for a farm.
It is.
So let's look at the 3 crucial rules the text gives us for dealing with this toxin.
Okay.
The first is that the wind is both your enemy and your ally.
Right.
It piles the scum onto one shore. So you have to keep your livestock and your pump intakes far away from that downwind bank and always draw your water from well below the surface where the scum floats.
The wind gives you a geographical advantage, yeah, if you use it right.
Right.
And the second rule is what we just deduced. Do not chemically kill the bloom while you are actively using the water.
Don't weaponize the dam.
Yep.
Got it. And the third rule goes against every basic survival instinct we have.
Which is?
Well, if we think water is contaminated, we want to boil it.
Oh, sure.
But boiling this water does absolutely nothing.
Nothing at all. Microcystin is incredibly stable. It easily survives boiling temperatures. And this resilience applies to basic physical filtration too.
Okay.
Letting the water settle or running it through a plain sand filter that will successfully catch the physical algae cells.
They are intact.
Exactly. But if those cells have already burst and the toxin has dissolved into the water, a sand filter does nothing.
Because the poison just slips right through the sand like salt dissolved in a glass of water.
Precisely.
So if boiling fails, and sand filters fail, and algicides create a toxic soup, how do we actually neutralize the dissolved toxin?
Well, to remove or destroy the dissolved toxin, you have to use advanced water treatment.
Oh, okay.
You need either powdered activated carbon, which physically absorbs the toxin so it can be filtered out, or you need strong oxidation.
Hold on, I want to clarify a word you just used. You said powdered activated carbon AD sorbs the toxin. With a D.
Yes.
Did you mean absorbs like a sponge?
No. Adsorbs with a D. It's a crucial difference.
Okay, lay it on me.
So absorption is like a sponge soaking up water. It takes it inside.
Right.
Adsorption is a surface phenomenon. The activated carbon has millions of microscopic pores.
Okay.
The toxin molecules literally stick to the surface of the carbon, almost like Velcro.
Oh, I see.
Once the toxin is Velcroed to the carbon powder, you can filter the carbon out and the toxin goes with it.
That makes so much sense.
Yeah. And the other option, strong oxidation, means breaking the toxin down chemically.
How?
Using meticulously dosed chlorine or ozone treatment.
Which brings us to the actual solution. We know the water is muddy, and we know it might be toxic.
Right.
Let's trace a single drop of water from that wild farm dam all the way to a safe drinking trough using the 5-step farm-scale treatment train outlined in the article.
Okay, let's do it. But remember, it is a non-negotiable sequence.
Right, the order matters.
This is the exact same treatment train that massive municipal waterworks use, just scaled down for a farm. The order is everything. If you skip a step or swap them around, the entire supply is compromised.
Okay, so the first hurdle for this drop of water is just getting out of the dam without bringing trees and mud with it.
Yeah.
Step 1 is screen and settle.
Your first line of defense is coarse screening at the intake pipe to block the big debris.
The easy stuff.
Exactly.
Yeah.
Then you route the water into a large settling tank, or you rely on the still dam itself.
To let gravity drop the heady silt out of suspension.
Right.
But gravity has limits. You let it settle, but you look at the tank and the water is still milky. It's holding on to that ultrafine invisible mud.
Right.
How do we get that out?
This requires step 2, coagulate.
Coagulate.
You have to force the mud to drop. You do this by dosing a coagulant chemical into the water.
Okay.
This coagulant acts like a chemical magnet. It attracts all those microscopic mud particles and binds them together into heavier clumps.
Right, making them bigger.
Yeah, which we call flocks. Once they clump together, they become heavy enough to sink to the bottom.
But how does a farmer know how much coagulant to use? Because treating 90,000 NTU river sludge requires a vastly different dose than treating 50 NTU dam water.
Oh, completely different. You find the specific dose using what's called a jar test.
A jar test.
It is exactly what it sounds like.
Yeah.
You take samples of your raw water in a row of glass jars, add slightly different amounts of coagulant to each, stir them, and just watch
Watch for what?
to see which jar forms the best clumps and clears the fastest.
Oh, that's brilliant.
Yeah, typically you are looking at a dose somewhere between 5 to 40 milligrams per liter.
It's literally like being a chemist in your own kitchen.
It really is.
Okay, so the coagulant has clumped the mud together and it's sinking, but we still have a tank full of heavy sludge at the bottom now.
Right.
If we just pump that, We're going to destroy the water lines. We need to physically pull that heavy mud out of the flow.
And that is step 3, filter.
Okay.
To catch that coagulated mud, you need a backwashing media filter. This usually utilizes either specialized sand or crushed glass. You run this filter at a specific flow rate of about 5 meters per hour. It does the heavy lifting of physically catching the flock.
Now, the source material also mentions those old, slow sand filters.
Oh, yeah.
The ones that run at just 0.1 meters per hour. Why not use those? They seem simpler.
Slow sand filters are brilliant, honestly. But they have a very narrow use case.
Which is?
They are fantastic for biological polishing on water that is already clear and stable. They're incredibly low maintenance.
Okay, so why not use them here?
Well, you only need to scrape the top layer of sand every 1 to 6 months on clear water.
Yeah.
But if you feed coagulated mud into a slow sand filter, it will clog helplessly in hours.
Oh, I see.
It simply cannot handle the physical load.
So a backwashing media filter it is.
Yes.
Okay, so the water has been screened, clumped, and filtered. The mud is gone. The water looks perfectly clear.
But it's not biologically safe yet.
Right. We need disinfection. Now, my first instinct would have been to just dump chlorine into the tank back at step 1.
A lot of people do that.
Why is that a terrible idea?
Because disinfection is step 4, and it only works on clear water.
Only clear water.
Chlorine is practically useless in muddy water because the organic matter in the mud simply consumes the chlorine before it can attack the bacteria.
So the mud basically eats the chemical.
Yes, entirely. The water entering the chlorine stage must be below 1 NTU.
1 NTU. Wow.
And you must dose enough chlorine so that after 20 minutes of contact time, you still have a free chlorine residual of at least 0.2 milligrams per liter.
0.2 milligrams per liter after 20 minutes.
Correct. And you have to verify this with a standard test kit. You cannot guess.
Now, the source also mentions UV light as an alternative to chlorine, but again, it stresses that the water must be perfectly clear. Why does UV care about mud?
It's fascinating, actually. It's because of microscopic shadows.
Microscopic shadows.
Yeah, UV light works by scrambling the DNA of the bacteria. But if there are particles of mud in the water, the bacteria literally hide behind the mud.
Are you serious?
The mud casts a microscopic shadow, the UV light misses the bacteria, and they survive to infect the herd.
That is wild. The bacteria literally use the mud as a physical shield against the light.
Exactly.
Okay, and speaking of invisible threats, what about the algae toxin? We mentioned the powdered activated carbon earlier. Where does that fit into the 5 steps?
Right, good catch. If you are dealing with a toxic algae event or even just musty tastes and odors, you add the powdered activated carbon back during step 2.
Alongside the coagulant.
Exactly. The carbon absorbs the toxin, remember, with a D.
Like Velcro.
Yes, it clumps up with the mud and then gets completely trapped by the filter in step 3, well before the water reaches the disinfection stage.
Okay, so we've screened, coagulated, filtered, and disinfected. The water is pristine and safe.
Almost there. There is one final crucial rule.
Which is?
Step 5. Cover the storage. If you leave treated water open to the sun in an open reservoir, you undo all your hard work immediately.
How so?
Sunlight strips chlorine out of water in a matter of hours. Yeah, and once that chlorine shield is gone, that same sunlight will immediately start growing a brand new crop of algae right there in your clean water.
Right.
Closed, dark tanks are absolutely mandatory.
It's like building a house and forgetting the roof.
Pretty much.
Okay, let's quickly summarize these absolute rules of thumb for the listener.
Right here.
Size your treatment for the dirtiest week after a storm, never the yearly average.
Right?
Watch the downwind bank for that green paint scum. Fence it off immediately, switch the supply, and remember boiling won't save you.
Crucial.
And finally, respect the sequence. Settle, coagulate, filter, and only then disinfect clear water, keeping it in a covered tank.
Yeah, because skipping a step isn't just inefficient, it's how a farm's water supply fails when it is needed most.
Right.
You know, think about how a drought fundamentally changes a farmer's relationship with their land.
What do you mean?
Well, in a good year with high rainfall, you are a livestock manager, a pasture manager. But when the drought hits and the boreholes struggle, you are forced to become a civil engineer and a water treatment plant operator.
You literally have to master jar tests and NTUs just to keep the lights on.
Exactly. The wind direction on a hot Tuesday suddenly dictates whether your dairy herd lives or dies on a Wednesday.
That's a heavy thought.
It shifts the entire farm's vulnerability. Your biggest risk is no longer just the soil or the grazing. The vulnerability moves to the sky, to the heat, and finally, it all narrows down to the last meter of pipe delivering water to the trough.
The last meter of pipe.
Yeah.
We've spent this whole time talking about protecting the herd from surface water. But as these droughts become more frequent and these algae blooms become more aggressive, it really leaves you wondering how long before this isn't just a livestock problem.
That is the big question.
If a farm's surface water is this volatile and this vulnerable to contamination, what does this mean for the groundwater tables and boreholes we're all retreating to next? If the dams are struggling this much, the aquifers below them are carrying an impossible burden.
A heavy burden, yeah.
Something to think about next time you turn on the tap. To everyone listening, please head over to the DWT website and dig into the knowledge base to read this article for yourself. Stay vigilant out there, respect the weather you are pumping, and we'll catch you on the next deep dive.